Today's webinar speaker is Andreas Fichtner. Andreas is an assistant professor for computational seismology at the Swiss Federal Institute of Technology in Zurich. His career has already taken him to 3 continents and 7 countries, and we are fortunate to currently have him back in the U.S. as the Blaustein Visiting Professor at Stanford University. His principal research interests include the development and application of methods for full seismic waveform inversion, resolution analysis and tomography, earthquake source inversion, seismic interferometry, and inverse theory. For his work, Andreas has received the Katie Award from the American Geophysical Union and the Early Career Scientist Award from the International Union of Geodesy and Geophysics. So without further ado, I will hand the connection over to Andreas to tell us more about his work in resolution analysis.
Thank you very much for the kind introduction and also for the opportunity to present this webinar. The work that I will present was done together with my colleague Christian van Leeuwen from Utrecht University in the Netherlands. I would like to start with a quote by Freeman Gilbert and George Backus that appeared in a paper that they wrote in 1968. It says that solving an inverse problem means to describe the infinite dimensional space of data fitting models. But basically, early on, they realized that any realistic geophysical inverse problem is ill-posed, and that solving the inverse problem is more than just fitting some data, but that it is actually the appraisal of this infinitely large space of models that fit the data acceptably well. That means solving an inverse problem requires resolution analysis. Now, the fact that we're sitting here today, 50 years later, indicates that we may not have been very successful in actually meeting the goals that have been set by Backus and Gilbert 50 years ago. And in fact, it seems that resolution analysis, instead of becoming easier, is actually becoming more and more difficult. And I would like to explain very briefly why that actually seems to be the case. Why is resolution analysis difficult, and why is it becoming harder and harder? I want to explain this with a very simplistic, but I think still illustrative example. We know from linear inverse theory that we have a linear relation between a true model, between a true Earth model of dimension n, and an estimated Earth model, ms, also of dimension n. And the relation between the two is described by the resolution matrix R, that loosely speaking tells us how the true Earth model that we have on the left-hand side maps into a smeared image ms on the right-hand side. Now R is a matrix, and it has dimension n times n, so the n squared, where n is the dimension of our model vector. Now, in the days of Backus and Gilbert, n may have been on the order of 100. That means in their days, so about 50 years ago, R was approximately 100 times larger than the actual Earth model that they wanted to estimate. Now, 100 times larger is already not insignificant, but it is something that you may have been able to compute and actually appraise and study with your human brain. Now, today, things have changed. Today, the number of model parameters that we have in realistic inverse problems may be 10 million or even more. As a consequence, the resolution matrix is not just 100 times bigger than the model that you actually constrain. The resolution matrix is now 10 million times bigger than your Earth model. And that has consequences. The first one is that we actually cannot compute R explicitly. And even if we were able to compute it, we would not be able to store it. The second consequence is that R is so large, it contains so many numbers that it has become virtually impossible to fully appraise the content of R with our limited human mind. So what we see and what we have seen over the past couple of decades is that as our data volumes, our computational power grows, we can for sure construct models of the Earth that are bigger and bigger. Instead of constructing Earth models that have 100 parameters, we may be able to construct Earth models that have 10 million parameters. But the problem is that while our computational power grows and while our Earth models grow, we step by step lose our ability to actually quantify the quality of our estimated impact. Simply because the size of R grows much faster than the size of the models that we construct. The immediate consequence of this is that we are really in desperate need of scalable methods that allow us to infer useful aspects of resolution. There are two emphases in this sentence. The first one is on scalable, the second one on aspect. We certainly need methods that don't only work for the problems that we have today, the problem size that we have today. We want to develop methods for resolution analysis that also work with the size of problems that we may have tomorrow, and with Earth models that may not have 10 million, but maybe 10 billion parameters. And also, since our resolution matrix becomes so large, it is clearly hopeless to try to fully appraise all the details of the resolution matrix. Instead, we have to learn how to extract useful aspects from the resolution matrix that are useful, for example, for the interpretation that we want to do based on the Earth models that we have inferred. Now, this brings me to the objectives of this webinar. There are basically two. I want to describe two methods to quantify resolution, to quantify the resolution matrix R, when this is too expensive to compute and too big to store. One of the two methods that I will describe is very simplistic and mostly intended to illustrate basic concepts, and it is strictly applicable to linear problems. The second one, on which I will spend more time, will be applicable to mildly nonlinear problems. And both are based on what is being called random probing techniques. Random probing is a very wide field in applied mathematics that basically deals with the extraction of information from matrices that are too big to compute and too big to store. Now, my first example to illustrate the basic concept of random probing. And it is about estimating the number of resolved parameters or estimating the trace of the resolution matrix R. And this goes as follows. The idea of this method is that we use random test models. So one of those random test models is MI. So M is the test model vector, and MI are its different components. And there may be many components, for example, 100 in Baxter's case, or 10 million in the cases that we may have today. And each component of this random test model, is random. It's a random number that varies from one realization of this test vector to another realization. There's not much that we ask from those random test models, except for two things. The first one, we require that the expectation of those random numbers, so if you will, the average of those random numbers as you average over many realizations, is equal to 0. So capital E of MI is equal to 0. If the average over single components, the average goes to 0. And also we request that the different components of the random model vector are independent, that they are uncorrelated. In other words, we request that the covariance of one component Mi and another component Mj is equal to delta Ij. Sorry, this symbol doesn't show up correctly. This very strange omega that you see here is actually intended to be a delta. So the covariance of Mi, Mj is requested to be delta Ij, the delta, basically the unit vector. So covariant, the components of the random test model are requested to be independent. Now then we have our resolution matrix R with components Ij, and we assume that this is too large to compute and too large to store and also too large to comprehend completely. So then let's let's compute the following quantity. Let's take our resolution matrix R and multiply it by one of the random test models, M. So we compute Rij times Mj, which gives us another vector of dimension n, dimension of the model space. Then we multiply this vector, Rij Mj, by this random model vector itself. Then, after computing this matrix vector product, we average over many random realizations. So we compute this matrix vector product not just once, we compute it many times for many realizations of random test models, and then we average over everything we get. Now let's see what that actually is. Now we know that Rij, so our resolution matrix, is a constant. It is the same for each random realization of the test models. And as a consequence, we can take Rij out of the expectation. So the expectation of Mi, Rij times Mj, is the same as Rij times the expectation of Mi times Mj. Let's go to the next step. Now let's insert some of the requirements that we had above. Now we know that the expectation of a product, so the expectation of the product of Mi and Mj, is the same as the product of the expectations, so the product of the expectation of Mi times the expectation of Mj, plus the covariance of Mi and Mj. In fact, what you see here in the second line is nothing but the definition of the covariance. But then we insert what we requested above. Above, we requested that the expectations of the individual random test vector components is equal to 0. So the first two terms go away. And we requested that the different components of the random test model are uncorrelated, that they are independent. And this means that our covariance of Mi, Mj is equal to delta Ij. Again, sorry for the symbol not showing up properly. So if you insert those requirements in the second row, you get that Rij is equal to, that you get Rij times delta Ij, which is the same as Rii, and that is the trace of R. So basically, this gives us a very simple recipe. We can compute the number of resolved model parameters, which is the trace of R, by simply averaging over many of those matrix vector products. And this method has been known for a long time. It's called Hutchinson's method, named after its inventor. As I said, the recipe is very simple. So basically, we do the following. We choose a random test model M, and we try to recover this test model in a synthetic inversion. That means we compute the estimated model Mest, which is the same as the application of the resolution matrix to this random test model. Then we multiply the result with the random test vector itself, this M transpose times M estimated, which is the same as M transpose times R times M. And this is exactly the quantity that we computed here. And then we average over many random realizations, over many realizations of random test models. And as a result, we get the trace of the resolution matrix. Note that in this whole process, the resolution matrix itself never had to be computed. And this is the beauty of the method. We know that R is too big to compute and too big to store, but nevertheless, we have a method to compute the trace of R, and all we require are products of R and M, and they can be computed very easily. That is the basic idea of random probing, that you use random test models or random test vectors in order to extract specific properties of a matrix that you cannot compute, that you cannot store on your computer. Now, following the developments of Hutchinson in 1990, many other authors, many other researchers came up with methods to extract different pieces of information from large matrices using variants of this random probing approach. And what you see here is a small list of references to different methods that can be used, for example, to extract not only to trace, but to extract, for example, eigenvalues of a matrix or diagonal elements, and so on and so forth. Now, what I want to show you in the time that I have left is a random probing technique that is specifically tuned towards resolution analysis in tomography. And it is intended to provide us with estimates of position and direction-dependent resolution levels. And I want to start also here with very simple intuitive examples. Assume we have a misfit functional chi that quantifies the difference between some observed and some synthetic data. And we make the assumption that we have found an optimal model M, for example, an optimal model of the Earth, that minimizes our misfit chi. In the vicinity of this optimal model M, we can express this misfit functional chi in the form of a Taylor series, and this is precisely what you see here. So our misfit chi evaluated at the optimal model M plus a small model perturbation delta M. This is equal to chi evaluated at the optimal model M plus 1/2 times delta M transposed times the Hessian matrix times delta M. The first order term that involves the gradient of chi is missing in this Taylor expansion simply because we assume that M is the optimal model, and the optimal model is defined such that the derivative of this misfit functional at the optimum is equal to 0. So that's why the first order term is missing, and we only see the second order term. Now, this Hessian operator that you see here is the discrete terms, the matrix of second derivatives. And this Hessian operator is also equal to the inverse posterior covariance, and a single column of the Hessian matrix is equal to a point spread function. So what is this point spread function? This point spread function is essentially the model that you recover in a tomographic inversion, in a synthetic inversion, provided that the input is a single spike, that is basically a delta function located somewhere in the model space. So you plug in the delta spike, for example, the point localized heterogeneity in S velocity, and you try to recover this point localized heterogeneity using your tomographic method. And what you get out is, of course, not the perfect spike, but you get a blurred version of this spike, and this blurred version is called the point spread function. Clearly, in any realistic problem that we're dealing with, H, just as the resolution matrix, is too expensive to compute and too big to store. But as we have seen in the example before, as we have seen in Hutchinson's method, we can actually infer properties of H, of the Hessian matrix, from its applications to random test models. And I want to show you how this works. Assume for simplicity and just for illustration that our point spread function, H, has the form of a Gaussian. This is exactly what you see here. It basically means that a single spike, so for example, the spike point localized S velocity heterogeneity, maps into a Gaussian blob. Under this assumption, we can explicitly compute the action of our Hessian to a random test model, which is this integral. So this integral is basically the continuous version of the matrix vector products that you have seen before. So we can compute H times a random test model, which is called here B. And this random test model is displayed right here. So it's basically a test model that has a different random value at every single pixel. Now H, Hessian, or the point spread function, acts as a smoother of this random test model. So what you get when you apply your point spread function H to the random test model V is a smoothed version of V itself. So you start off with this random test model where you have a different value at every single pixel, And after the application of H to this random test model, you get a smoothed version of the random test model itself. Now, what you see already from this is that obviously this smooth version of our random test model has some characteristic length scale. And in fact, those characteristic length scales that you see in those oscillations of the smooth version of the random test model, they contain information on the length scales of H itself. And the question is, how do you actually extract the width of this point spread function from the characteristic length scale of this smooth random test model? And in fact, this can be done very easily by computing the autocorrelation of H itself. So the recipe here is very simple. Let's go back one slide. You compute the smoothed version of the random test model. Then you compute the autocorrelation of the smoothed version of itself. And then you average over many random realizations. And the outcome is what you see in this plot. You see that basically the strength of the colors, the darkness of the colors symbolizes over how many random realizations we averaged. The very pale one that you see is just for a single random realization. What has been done for the very pale one is just take one random test model, apply to the Hessian, and then compute its autocorrelation. And as you get to the darker colors, you do exactly the same, but you average over many random test models that you have chosen. And what you see is that as you go from 1 to 2, 3, 5, 10, 20, 50 samples, you get to the darker and darker colors. And eventually, the autocorrelation of this Hessian test model product converges to the black Gaussian that you see here. And what you can show is that the width of this autocorrelation function, as you see here, is equal to square root 2 times the width of the Hessian, which is square root 2 times the width of the point spread function. So what that means is that you can actually estimate the width of the point spread function, you see to the right, from those Hessian vector applications. And in this figure, you see those estimates for cases where you only use one random test model, where you use two, and so on and so forth. And you see that if you use more and more random test models, you get better and better approximations for the width of the point spread function. Now, the interesting thing to observe here is that this autocorrelation function itself takes a long time to converge. You see in the very pale version, where only one random test model has been used, those oscillations appear throughout the domain, and it takes a long time until those oscillations have actually gone away, until they have converged towards the black Gaussian. But at the same time, you also see that the central peak of this autocorrelation function converges extremely quickly. And this is in fact something that you can prove mathematically. The convergence rate of this autocorrelation function in the vicinity of the central peak is very high, and that's why you need only a very small number of random test models in order to approximate the central peak and to approximate the width of this point spread function. If you want to get only the width, there's no point in using 50 random samples, because already with a very small number of random samples, you get a very good estimate of the width. And this is basically what this method exploits. It's the fact that you get very fast convergence of this autocorrelation function around the central peak. Now, that brings me to some very preliminary conclusions. The first thing we see is that, or that we saw, is that the Hessian acts as a smoother of random functions. The Hessian is a point spread function, and this point spread function smooths random test models that we apply to it. We have also seen that the smooth functions carry information on resolution. We can actually, from those smooth functions, extract the width of the point spread function using autocorrelations of this Hessian random test model application. Concerning convergence, we have seen that the correlations themselves, or those autocorrelations themselves, may take a very large sample size or a very large number of random test models in order to converge. But the interesting thing is, and the key point here is that the width of the correlation function, the central peak of this correlation function, converges extremely quickly. As I said, this is something that you can actually prove mathematically. It's not just empirical. And as a consequence of this, we know that useful resolution proxies may be obtained with actually a very small number of random test models. Now let's carry this a little bit further. So far, this was just an intuitive example to convey the basic principle. Now let's see if we can apply this to a still relatively simplistic synthetic full waveform inversion in 2 dimensions. We chose to apply this method to full waveform inversion because it is currently the most expensive, computationally most expensive tomographic method. If we develop a method that works for full waveform inversion, we are quite confident that it will work for methods that have lower computational requirements. So the setup of this synthetic full waveform inversion is the following. We have a target model that is shown here in the upper left. The black dots, they are receivers, and all the black crosses, they are sources. If you will, they are the earthquakes. And you see here the target shear velocity model. You see to the left, shear velocities are higher, about 3.7 kilometers per second, with small variations superimposed. And on the right, the shear velocities are a bit lower, again with small variations. The initial model that you see in the center is more homogeneous. It has homogeneous velocities on the left, homogeneous velocities on the right, and the panel that you see here on the right is basically the final model that we obtained. So this is our full waveform tomographic model that we obtained when we tried to recover the target model that you have here to the left, starting from the initial model that you have in the center. Just to show you this a little bit more clearly, what you see below are not absolute velocities, but velocity perturbations. So here you see S velocity perturbations of the target model. These are the S velocity perturbations of the initial model. And these are the S velocity perturbations in the final model that we reconstruct using this 2D full waveform inversion. You see there are some structures in the final model that indeed correspond pretty well with some of the structures that we have in the target model, and clearly there are other regions that are very poorly reconstructed. Now, what we will now do is we will apply random test models to the Hessian, which we can do very efficiently using second-order adjoints. And then we will compute autocorrelations of this Hessian random test model application locally in different directions. And from this, we will be able to estimate, or we are able to estimate the width of the point spread function in different directions. And what you will see here, or what you do see here, is the estimated width of the point spread function in x1 direction, which is basically here the horizontal direction. And this width of the point spread function, this is what we call the resolution length. Now, what do these figures show? The figure to the left shows our estimated resolution length for the case that we have one single random test model. So we take one single random test model, apply this to the Hessian using second-order adjoints, and then we locally autocorrelate this Hessian vector application with itself in x1 direction. You see it looks still a little bit patchy. There's some resolution lengths that are very large. And then we start averaging. So instead of doing this procedure only once, we choose another random test model applied to the Hessian, autocorrelate, and then add it to the result that we had before. And we take the next random test model, repeat exactly the same procedure, and so on and so forth. And in the center, you see the result after doing this 4 times, that is with 4 random test models. Of course, you can do this for many more. This is for 10 random samples, and so on and so forth. And after a while, you see that this picture, that those estimates of resolution length in x1 direction stabilize. Now, what does this figure show? It shows that resolution is very heterogeneous. When you are in one of the dark regions of this figure, that means that you are in a region where resolution length in x1 direction, this resolution length in horizontal direction, is on the order of about 40 kilometers. That is, you put a single spike of velocity heterogeneity at that position and try to recover it using this full waveform inversion, you will get a blurred version of this spike that is about 40 kilometers wide. However, if you go to a slightly different position further down here, then you see we have lighter colors, and their resolution length in x1 direction is about 150 kilometers, so more than 3 times larger than what we had before. That means that the spike that we plug in will not map into an anomaly that is only 40 kilometers wide. It will smear into an anomaly that is 150 kilometers wide. What we also see from this example, apart from the physical interpretation, is that it takes only about 5 to 10 samples to get those estimates of resolution length to converge. And it goes so fast because of this very nice property that we have seen before, that the central peak of this autocorrelation function converges very, very quickly, even though the details of those correlation functions may take a very long time to converge. All we need for those estimates is indeed the width of the autocorrelation function that converges extremely quickly. Now, what you have seen here is correlation length in x1 direction, that is in horizontal direction. But of course, you can also compute those autocorrelations in a different direction, for example, in x2 direction, which is the vertical direction here. And then what we get is basically a similar figure. If we use one random test model, we get the patchy image to the left. If we average over 4 random test models, you see that you find the figure in the center, and so on and so forth. The one to the right is the estimate of resolution length in x2 direction for the case that you use 10 random test models. You have a similar interpretation as before. When you're in regions where you have the dark colors, you have a resolution length that is very short, you have very good resolution, about 40 kilometers in this horizontal direction. If you're in one of the white regions, resolution is very poor, or at least not as good as in the dark region. You see, and that is always an eye-opener when you look at this, that resolution itself is very, very heterogeneous. So there's no point in saying that the tomographic model has a resolution of x kilometers, because this resolution varies very rapidly as a function of space. Let's go to a position that is slightly different, and resolution can be much better. Okay, so let's continue a little bit. What you have seen before was synthetic. It was a synthetic full waveform inversion in 2 dimensions. Now let's see if this actually works with real data. So what we did here, we looked at a full waveform inversion in the Western Mediterranean, which is a very interesting area to study, basically for 2 reasons. The first one is that the tectonic evolution of the Western Mediterranean is not very well known. We're still missing pieces of earth structure, for example, the geometry of subducting slabs in the Western Mediterranean region. The second reason why this is a very interesting region is that there's a recent deployment of a very dense station network, that is the Bear Array and a few other stations, and that is basically what you see in this figure. All the black triangles, they are seismic stations that have been installed on the Iberian Peninsula and also in Northern Africa. And of course, this is complemented by seismic stations that have been installed in other places of Southern Europe, in Greece, in Italy, and so on and so forth. In this full waveform inversion, we use data from 52 earthquakes that were recorded in that region by more than 1,000 stations, many of those from the array. In the inversion, we used all the pieces of data that we could get our hands on or that we found useful. That includes body waves, fundamental mode and higher mode surface waves, and so on and so forth. The periods range between 10 and 150 seconds. The forward model was based on a spectral element discretization of the seismic wave equation that we coded up in a spectral element solver that we developed ourselves and keep maintaining, and that is meanwhile running on GPUs in production mode. And with this spectral element solver, we can model seismic wave propagation in 3D, viscoelastic, and anisotropic earth models. The inversion is based on, or starts from an initial model that comes from a previous full waveform inversion for Europe and Western Asia, and the optimization is driven by the conjugate gradient method that uses gradients computed via the adjunct method. In this inversion, we invert for DSH, DSV, VP, density, and the source location effect. So it is an interesting multi-parameter problem. I only want to show you very briefly what this model looks like. We're looking here at the isotropic S velocity at a reference frequency of 1 Hertz. The color scale is a little bit unusual because I tried to display cluster velocities and mantle velocities at the same time. Cluster velocities are shown in grayscale from white over gray to black, and mantle velocities velocities of 4 kilometers per second upwards. Here are displayed in colors from red over white to blue. When we look at 5 kilometer depth, in the upper left panel, we see clearly cluster structure. For example, we see low velocity anomalies. This is the Guadalquivir basin. You see the Po basin, the Rhone Valley, the Molasso basin, and many others. The Massif Central is located here. You see the Alpine Arc, and so on and so forth. If you go a little bit deeper, for example, to 25 kilometers, you see that most parts of Europe, Asia, and Africa are still continental, but you have this little patch in the Mediterranean where at 25 kilometer depth, you're already in the mantle because you have essentially an oceanic region. If you go to 40 kilometers, you see that the deep roots of many European origins show up. For example, you have the Apennines, the Alpine Arc, the Dinarides, and so on and so forth. The Batics right here. So the model seems geologically plausible. We go a little bit deeper into the mantle. Here we look at isotropic S velocity variations. You see, for example, at 300 kilometer depth, a very strong imprint of the Mediterranean subduction system. So all the blue colors are basically subducted slabs. This talk is not so much about the geologic interpretation of this model. I want to talk about resolution analysis. I will largely skip those vertical cross sections that you see here. And this is what this resolution analysis looks like. So it follows exactly the same recipe that I introduced before. You run your full waveform inversion or whatever inversion you're running towards an optimal model. And once you arrive at this optimal model, you apply the Hessian to random test models. Once you have this Hessian random test model application with the help of second-order adjoints, you autocorrelate the output with itself. And you autocorrelate in different directions. You autocorrelate in north-south direction if you want to get the width of the point square function or resolution length in north-south direction. You autocorrelate in east-west direction. You want to have resolution length in east-west direction, and so on and so forth. And of course, you can do this for different points in space. At every point, you compute a local autocorrelation that is centered around that point. And this is what you get. In the upper left, we see resolution length in north-south direction at 50 kilometer depth, for example. And you see very clearly that in that region, where we had the very dense deployment of seismometers of the Iberian Peninsula and Northern Africa, resolution is very good. and resolution length approximates or approaches about 30 kilometers, which is very close to the minimum wavelength that we have been able to use in this full waveform grid. So here, resolution length, at least in north-south direction, is actually very good. That this is 30 kilometers basically tells you that two point localized heterogeneities have to be separated from each other by at least 30 kilometers in order to be visible as two separate heterogeneities instead of blurring into one block. But as in the synthetic 2D example, we also see that resolution itself is very heterogeneous. If we go, for example, to the south central Mediterranean, you see here in the white gray colors, there resolution is not about 30 kilometers, it is actually closer to 300 kilometers. And that is a very simple consequence of the poor coverage that we have in the south central Western Mediterranean as a consequence of not having many earthquakes and not having many stations. And we can compute this resolution length also in other directions. So in east-west direction, this gives you the width of the point per function in east-west direction, or the distance by which heterogeneities have to be separated. And one can also compute this for the radial direction, basically by computing autocorrelations in radial direction. And here's an interesting aspect in this figure. You see that those horizontal resolution lengths, in north-south direction and east-west direction, they are somewhere between 30 and 400 kilometers. So in the well-covered regions, say it's about 100 kilometers. But for the radial directions, this looks very different. For the radial directions, it seems that resolution length is more homogeneous and it's also shorter. So you have better resolution in radial direction or in vertical direction. And the simple reason for this is that this full waveform inversion that we have been running is dominated by surface waves. Those surface waves, as you see in the horizontal resolution length, they may not be very good in constraining where a heterogeneity is located laterally. However, by using fundamental and higher mode surface waves, you still have a pretty good idea of the depth where those heterogeneities have to be located. And as a consequence, resolution in vertical direction tends to be significantly better than resolution in the horizontal directions, and it can even be pretty good in regions where resolution in the horizontal directions is actually not very good. So this can be computed not only for 50 kilometers, but also for any other depth. So that brings me to my conclusion. First, I want to mention some limitations of the method that I have presented. And the only really significant one that we could come up with is that it is a local analysis. So what this means is that this whole resolution analysis operates under the assumption that you actually found the optimal model, or at least a very good approximation of the optimal model. What this resolution analysis does not do, it does not tell you if you actually landed in the right minimum, or if you may have landed in a completely insignificant local minimum. This is something that resolution analysis, at least as we have introduced it here, does not tell you. So this is a limitation that we clearly have. But there are many benefits. The first one is that you can quantify spatial resolution and also interparameter trade-offs. I have not shown the interparameter trade-off part here because that would have taken too much time, but you have seen that with this very simplistic method, we have been able to quantify resolution in the form of position and direction dependent resolution lengths. Another benefit are the, sorry for the numbering, this is also something that obviously got messed up. Another benefit are the very low computational costs. So what you have seen in those experiments is that around 5 Hessian model applications are sufficient to obtain useful results that can be interpreted. Of course, one can also always do more, but after applying the Hessian, to 5 random test models and autocorrelating, you usually obtain results that are already pretty stable. Now, those 5 Hessian model applications, they are, from a computational perspective, equivalent to approximately 5 conjugate gradient iterations. Now, let's put this a little bit in perspective. So, today's full waveform inversions that we run in practice with real data, they require about order of magnitude tens to hundreds of iterations. It depends very much on how heterogeneous the model is, and so on and so forth. Typically, in seismological applications, we use 20 iterations. In industry applications, this might be several hundred. The point here is that this resolution analysis has much lower computational requirements than the solution of the actual optimization problem. And that really puts resolution analysis a little bit upside down. Most resolution analysis methods are actually much more expensive than the solution of the optimization problem. But here you actually have a method that is computationally less expensive. Another advantage is the very low algorithmic complexity. Basically, this resolution analysis method is extremely easy to implement, and it works basically without doing any modifications to existing codes. So once you have a full waveform inversion machinery, for example, that works using adjoint methods, you can very easily compute those Hessian model applications and perform this type of resolution analysis. Really, no modification of the code itself is required. It's just mainly building a few scripts around it. Another one is scalability. This is empirical. This is nothing we can prove, but we have seen that around 5 random test models are sufficient, no matter if we work in 1, 2, or 3 dimensions. Empirical, no proof. This is just what we have seen in numerical experiments. And another beauty of this method is that even though we applied it first to full waveform inversion, because this was the most expensive method we could come up with, it is still applicable to any tomographic technique. Can, for example, be applied to the resolution matrix that you have seen at the beginning. So this brings me to the end. Again, sorry for the small inconsistencies that we have seen in the notation and the small errors that come from incompatibilities of Adobe and PowerPoint. Yeah, so thanks for your attention. I'm happy to take questions.
Thank you. I see a couple of people actively typing in the chat window, so we have a couple of questions coming your way. Oops, it got cleared out. While we're waiting, just remind people that the recording of this event and actually the slides can be found on our website. So if you want to go back and look at any of the slides and some of the references, that will be in that document.
Okay, so thanks, Min, for the question. So how to generate these random test models? So basically, we really just generate them with a random number generator. So our Earth models, they are gridded, or they have pixels, and we simply assign different random values to the different pixels. There's nothing more than that. And yeah, that's really just it. It's literally generating a random test set.
Seems to me there's probably also some art in picking the width of your autocorrelation function.
Sorry?
It seems to me that there is some art to picking the width of your autocorrelation function.
So that is so basically what you do. You compute local autocorrelation. So that is not the autocorrelation of the whole output with itself, but you pick basically windows around a certain point in space, and you compute an autocorrelation within this window. And from this autocorrelation, you get the width of the point spread function for that point around which the window is centered. And indeed, that requires some, I would say, some prior knowledge on the maximum resolution length that you expect. For example, if you expect that your resolution length is on the order of, say, 100 kilometers, you should not pick an autocorrelation window that is 10 kilometers high. And that is something that needs a little bit of experimentation. So what we basically do is we make an initial window width to compute those local autocorrelations, and then we increase it step by step, basically stop increasing it once we see that we have stable results. Does that answer the question?
Correct. So you're saying that it is static over your model space. That you try variations of the autocorrelation functions over your model space, but at the end of the day, it's a static.
Exactly. We try different correlation. We try different widths of the correlation window, because it's a local autocorrelation, and we basically have to define what we mean by local.
So you've applied this to your European model set. Have you run other models with this technique?
Actually, yes. So we have applied it to various models. So these are in the process of being published. One was to Japan, which basically worked in exactly the same way. It's directly used basically the scripts that we have developed for this. And yet another one is Eastern Anatolia around the Sea of Marmara. So these are the ones to which we have applied it so far.
So you're finding
sorry?
So are you finding in general your level of resolution is very heterogeneous?
It is generally very heterogeneous. And I think this is something, it's not only a problem in, say, regional to global seismology. It's simply that our coverage is so heterogeneous that resolution itself has to be extremely heterogeneous as well. And this is a big problem in the interpretation of those tomographic models that I think not many people are aware of. Basically, we know that we introduce artificial structure, or say artificial texture, in our tomographic models by having resolution that is very strongly variable. And that is something that one needs to keep in mind. And I think this is something that really complicates geologic interpretations of the models that we produce. I don't think we are currently able to take this into account in a very good way.
It seems to be able to find a technique to able to visualize the resolution along with the velocity model to pick out.
That is something one would need.
Yeah, yes. A good way to doing that is key, to be able to really be sure about the structures you're interpreting.
Yeah, this is actually an interesting aspect. For example, people in medical tomography have realized, I think much earlier than we have. What people in medical tomography do is they do not design devices that optimize resolution, or that basically achieve the smallest possible resolution length. They design devices that produce a resolution that is as homogeneous as possible.
Interesting.
Simply in order to make sure that you don't introduce this artificial texture through the heterogeneity of resolution.
Interesting. It'd be interesting.
Yeah, here's another question. I wonder how to take advantage of the lateral and radial resolution length you obtain. I mean, should we say the model with very long resolution length not reliable? So taking advantage of those resolution lengths, I think really comes at the stage where we interpret those models in terms of geology or whatever we are interested in. And I would not say that parts of the model their resolution length is long are completely unreliable. They are less reliable, and they have to be interpreted in a different way. So yeah, I think taking advantage is really at the interpretation stage. Okay, there's another question. Can you smooth the model with resolution length? Yes, so that is something one could do. You could, for example, say you pick the longest resolution length that you have, and then you smooth the whole model to that length scale. That is something one could do, and one would obtain a model that is smoother, but has a more homogeneous resolution length. So it would have the benefit of being more easily interpretable, because it won't have those artificial textures introduced. But on the other hand, it's clear that you lose detail. So you pay a price for the homogeneity of resolution length. Yeah, but it's a good idea, and it's something that one can do. Is there any way to visualize the model parameter trade-off? Yes, there is. So that is the part I did not talk about. But what you can also quantify is or maybe I could. So, by parameter trade-off, do you mean trade-offs between different physical parameters? So, for example, between p velocity and s velocity? Yes. Okay. So yes, that can be quantified, actually in a very similar way. So what you can do, for example, is you take a random test model that has random variations only in s velocity and no variations in p velocity. And then you apply this to the Hessian. And then the Hessian will tell you how your random s velocity heterogeneities map into random p velocity heterogeneities. So what you can then do is you can autocorrelate the p velocity part of this Hessian model application and basically get two things. You can get the width of those point spread functions that come from the mapping of s velocity structure into p velocity structure. And you also get the height, or say the strength of those point spread functions. And when you plot this, you basically get the strength or the magnitude of the trade-offs between s velocity and p velocity structure. So so the answer is yes, it can be done in pretty much the same way. The only difference is that you don't autocorrelate the s velocity input with the s velocity output, but you autocorrelate the s velocity input with the p velocity output, and that's basically it. So yeah.
Great, we're approaching the end of our hour. We've had a lot of good questions. I want to again thank Andreas for his time today, and thank you everyone for participating in today's webinar. Everyone have a wonderful summer of research and travel.